Hello and welcome to this video lecture on Chapter 5. Today we'll be talking about probability and modeling uncertainty. So if we look at uncertainty and then we look at decision making, this is the part of the decision making model that managers have the least amount of information to deal with. So anything that we can do to provide some helpful insights into whatever decision they're making, that's going to reduce that risk or the uncertainty. And we do that by trying to provide the probability that something is going to occur. So if you look at this definition here, we have the probability as the numerical measure of the likelihood of an event that will occur. And we can use this measure of probability and communicate that through a probability distribution. And once we know the probability distribution of the data that we're looking at, then we can make some additional insights into that. And because of that, that'll help the decision maker evaluate different alternatives or actions and then determine the best course of action. So we're going to continue on and talk about events and probabilities. And so when we have an event, we are usually doing a random experiment. And the random experiment is a process that generates a well-defined outcome. And so when we specify all the different outcomes that could occur in this experiment, we call that the sample space for a random experiment. So a random experiment example might be a coin toss or a rolling of the dice. Then an event is defined as the collection of the outcomes. What did we find? So I want to step back just for a moment and think about probabilities and probability distributions. We know that in a coin toss, the probability distribution is binomial, and we'll get to that here shortly. But what that means is, okay, you've got one of two outcomes. Either it's heads or it's tails. But if I flip that coin 100 times, 1,000 times, I would expect that it would be very close to 50% heads, 50% tails for the outcomes of all those different tosses. If I find that it's not, then from that probability distribution, I can then determine, okay, this coin isn't following that normal distribution, so there must be something amiss. So maybe it's weighted on one side or the other or something else. You might find this more with the rolling of dice or a die. If you roll a die, if it's purely random and each side has an equal chance of coming up, then if I do this 1,000 times, then I should have an equal number of each side appearing. If it's not, then something has skewed that outcome. If I look at my probability distribution, I can say, well, it should be this, and if it's not, what's the likelihood that it didn't fall within a certain range? If I know that is greater, then I can say that there's a significant difference from the distribution that I think that die and those outcomes should have. So I just wanted you to understand, why we're looking at distributions and models. They give us what a random event should look like if we plot it out. And then from there, we can determine, okay, is our outcomes part of that randomness? Would it fit into that distribution, or something else going on? And then from there, we can help people make decisions with that. So here we have some random experiments and the outcomes. So we've talked about the first two already. Another one might be if you do a sales call, what are the outcomes, possible outcomes? They would be either to purchase or don't purchase. What are the outcomes if you do buy a particular stock and hold it for a year? There are three outcomes. Either the stock goes up, the stock goes down, or it stays the same. Then there's another experiment you might do, reduce the price of a product. What might happen then to demand? Either it goes up, it goes down, or there's no change in demand. So let's go through the example in the book. We've got a company, California Power and Light Company, and they're starting a project that's going to increase the capacity of one of its plants in California. They'd like to know what's the probability that it can finish in 10 months or less. From previous projects, they've compiled the following information. So they had different projects that were completed in 8 months. There were only 6 of those. 9 months, 10 of those, 10 months, 12 of those, and so on. So they had 40 projects altogether. So what's the probability of 8 months? That would be 6 divided by 40, or 15%. 9 months, 10 divided by 40, or 25%. So you can see this is very similar to the frequencies that we were calculating before, except now we're not calling them frequencies. These are now probabilities. So the probability of an event then is equal to the sum of the probabilities of outcomes for the event. So if we want the probability of 10 months or less, we would just sum the probability of 8 months, the probability of 9 months, and the probability of 10 months. So that's 15, 25, and 30, and we could say the probability of completing this project in 10 months or less is 70%. So again, if we look at these numbers, it's very similar to the cumulative probability, which would be 15, 25, and 30. So this would be 70% here. 11 months or less then would be 85%, and 12 months or less we would be at 100%. Okay, some basic relationships of probability that you need to understand so you can apply these and answer different types of questions if you know these rules. One idea is called a complement. So if you have a completion of an event, then you have to think about its complement as well. And a complement is defined to be the event consisting of all outcomes that are not A. So if we look at figure 5.1, and this is a Venn diagram, when we see that, we've got event A and the complement of event A. So everything that's not A. And then all our outcomes, this is the sample space. I think we covered everything here. Right. Another way of thinking about this is that the complement of A is 1 minus A. So if event A has a probability of 30%, then the complement of A is 1 minus 30%, or 70%. Take a moment and let that sink in, because this idea of just doing the simple 1 minus A can catch you on a lot of different problems. It's just that simple in order to get the complement and work from the complement when you're doing certain things. So when you're doing any kind of probability application, either event A is going to occur or its complement is going to occur. So when you solve for the probability of A using the complement, that's what this is saying, and that's what I just went over. So if I know the complement of A, then 1 minus that complement gives me the probability of A. So based on what I just said, if I know that 70% is the complement of A, then A must be 1 minus 70% or 30%. Next thing I want to talk about is the addition law. So that's very helpful when you're interested in knowing the probability that at least one of two events will occur. So some concepts then that are related to this combination of events is the union event and the intersection event. So when you write this out, I typically will remember that when you do a U, that's the union, so this other one must be the intersection. So you'll see that, and we'll see that here shortly. So if we do the union of A, event A, and event B is defined as all the events containing all the outcomes belonging to A or B or both. And you usually see it written out like this, A union B. So the diagram on the next slide shows the union of A and B. So it typically will represent the event A as a circle and event B as a circle, and then you also have the intersection portion. So this is a Venn diagram. So we have event A, event B, and this is the sample space. So this is event A, this is event B, this would be the intersection of A and B. But right now, this is A union B. So everything that's blue is A union B. So it's everything in A, everything in B, and everything that's intersecting. When we talk about the intersection, that is intersection of event A and event B, that is the portion where both events belong to both A and B. And you usually see it written like this, A intersection B. So this area right here is A intersection B. Sometimes you want that information, but you're only given this information and this information. So some basic algebra with the addition law, and this is a way to compute the probability that event A or event B or both will occur. And we use that to compute the probability of the union of two events. So the probability of A union B is the probability of A plus the probability of B. Think about that. So for our two circles, we got probability of A, probability of B, minus the probability of A intersection B. So if I could draw that out using our Venn diagram. Okay, we got A here, we got B here, and this is the intersection. So we've got this probability of A, probability of B, and we're going to eliminate the intersection portion. And that gives us the addition law. And then we have special case for mutually exclusive events. So the occurrence of one event precludes the occurrence of the other, or if the event has no outcomes in common, then there's no intersection. And if there's no intersection, then the probability of A union B is just the probability of A plus the probability of B, because the intersection is 0. And so, I mean, just thinking about that and just drawing it out will help you keep that in mind. The next thing we want to talk about are conditional probabilities. So these go for independent events, multiplication law, and Bayes' theorem. So that's what we'll be covering next. So let's define conditional probability. And that occurs when the probability of one event is dependent on whether some related event has already occurred. So the example your book uses is a savings and loan mortgage default risk problem. So what we want to know is whether the probability of a customer defaulting differs by marital status. The data file is called mortgage default data, and I'll make that available to you once we finish this lecture. So you open it up and it'll look similar to this one. There are about 300 home mortgages for customers in there, and it was historical data, so they tracked whether they defaulted on the mortgage or not and whether they were single or married. So one of the first things you'll want to do is create a pivot table, and the pivot table will have marital status as your rows and then whether you defaulted or not. And so once you have that, you can then determine what the probability that a customer defaults on his or her mortgage is. 120 divided by 300. So here's the default, and we've got a total of 120 out of those 300 total defaulted, so 40%. So the probability the customer does not default on his or her mortgage is, remember that 1 minus the complement, so we got 60%, or 180 divided by 300 here. So if we create that pivot table, I would suggest that you go ahead and try and do that. It'll look like similar to this. Notice what marital status is in the row. We've got the default on mortgages in the columns, and then we're counting the numbers here. So I've got the same answer here. So if you look at that, you can see, I bring that. You got marital status here, you got default on mortgage at the top, and they just change those, and then the count of the customer number. So that's this field right here. So the next thing we want to continue with is, how do you calculate the conditional probabilities? So if we look down here, we've got the probability of A given that B occurred, or the probability of B given that A occurred. So when the values give the probability of the intersection of two events, the probabilities are called joint probabilities. So the joint probabilities, if we go back to this table here, what's the probability that there's no default and they're married? No default and they're single, default and married, default and single. Those are your joint probabilities. Marginal probabilities are found by summing the joint probabilities in the corresponding row or column. And you can also calculate them. We just calculated the marginal probability of no default and default, but we didn't calculate the marginal probability of married and single. So the conditional probabilities then are computed as a ratio of joint probability to a marginal probability. So if you would, so the probability of A intersection B divided by the probability of B. So think about this. So whenever you're doing a conditional probability, you're going to do an intersection of the two events and divide by whatever event that you're given, that's a given. So it occurred already. So if this one's B, then it goes in the denominator. This one's A, it goes in the denominator. If we look at what the book has, then you can see the joint probabilities are these percentages or probabilities. We calculated these two already. Those are marginal probabilities. So we take up, whatever our numbers were, which was 180 divided by 300. That's where we got this 0.6. This was 120 divided by 0.4. This will be equal to 143 divided by 300. This is 157 divided by 300. All right, so I have this information. I can calculate it from my original table, the crosstab table. And that is, give me a second here. Right here. So we're just pulling that information out of our main table, those 300 mortgages. And I think I need to bring this back here. That's what we were talking about. Let me did that. And this is what I was talking about earlier. Sorry for the not having it on the right screen. And I can repeat it here. So what we've got here, again, conditional probabilities. So A given B or B given A. And so we have, it'll always be the intersection of the two events. So probability of A given B, and then whatever is given here goes in the denominator. And then the marginal probabilities are found by summing the joint probabilities in the row or column. And what they're just saying there is, instead of calculating it out directly by knowing the total number divided by the total grand total here, we could just sum this probability and this probability to get this probability. Or this probability plus this probability gives us this probability. Same for these two going down. So going across the row, I'm going to get the same total here. Going down the column, I'm going to get the same total probability here. Now I can also get these numbers by looking at my pivot table. So I'm back on my pivot table. Hopefully I will remember to put it back on the regular slides here. What you'll want to do is you'll have your pivot table and you'll want to right click on here. And you want to do show value as percent of parent total. And you can change that to whatever you want. Now we see that this is not correct. So it means I chose the wrong one on purpose here. What I need to change this is to percent show value as percent of row total. And it's not percent of parent row total, it's just percent of row total. And then we get those same percentages that we have that are shown in your book. So this value right here, 55.24%, says what's the probability of defaulting given that you're married? It's 55.24%. So if you look in your book, then how was that calculated? So it was easy to do that on a pivot table. But what they did in your book is, if we go back, if I reset this, show value as no calculation. So we want to get the joint probabilities. And joint probabilities are show value as a percent of grand total. So here are the joint probabilities. And then on the outside here, we see the grand totals. So the probability of D given M, right, is the intersection of D and M. So yes and married, so that's the intersection. So we have this value divided by, and then the probability of M, which would be our grand total for that row, and that's how we came up with that. Now, if you're on page 175 in the book, that's the numbers. This number divided by this number gives us the probability of default, given that you're married, divided by the probability of being married out of all of our data. And if I change this back to show value as percent of row total, that gives me the same number that we had there. Okay, so work your way through that, see if you can answer some questions or think about it. You know, what does this value here, 26.11? The probability of defaulting if you're single is 26.11%. The probability of not defaulting, given that you're married, is this amount. The probability of not defaulting, given that you're single, is 73.89%. So if I was a bank loan officer, I'm way more inclined to provide a loan to a single person, just given the data that we've just looked at. Now, in the real world, they're going to look at a lot more different items than just being single or married. We'll pause there, and when we come back, we will pick it up with conditional probability of independent events.